All right, for part 4 here of chapter 16, it's going to be probably the shortest of the 5 parts from this chapter, but it's got 2 really important reactions plus a really important idea, protecting groups. So let's jump into it. And 16.10 talks about protecting groups, which is something you need to consider if you've got multiple functional groups in a molecule, but you're trying to do something and you've got one of those groups that you don't want to react. And if you don't do anything, it would react, right, with both of your functional groups. Okay? So a functional group, right, or sorry, not a functional group, a protecting group, which is what this section's all about. You know what functional groups are now. A protecting group, right, is a group that goes in and protects a functional group from some sort of synthetic operation that, if left untouched, the functional group wouldn't otherwise survive. Right? So a different way to think about it is if you have multiple functional groups, but you only want one of them to react. Okay? One of the things that we can take advantage of to make a protecting group is what we saw in the previous video, forming acetals. Okay? Ketones and aldehydes can react with Thiols, okay, and form a cyclic acetal. So where is that useful? Let's look at a protecting group here on slide 88. Okay. For this synthetic transformation up top, I've got a ketone and I've got an ester. And I want to reduce the ester down to an alcohol, but leave the ketone unchanged. Okay. So you can reduce an ester down to an alcohol with lithium aluminum hydride, right? We've talked about that reducing agent before, but the ketone is actually more reactive than the ester is, okay? So if I didn't do anything else, I would harm that ketone as well and take it down to a secondary alcohol. So the order of operations is important, right? First, I take my molecule and expose it to my diol to form this 5-membered cyclic protecting group, which is stable. Okay? Then I do my reduction, and I won't reduce my acetal with lithium aluminum hydride, but I will reduce my ester, okay, down to an alkoxide. Then the acid both protonates the alkoxide to an alcohol, and acid catalyzed hydrolysis, right? We hydrolyze the acetal, which was also mentioned in the previous video, back to a ketone. And then, sure as that, I got my molecule. Okay. This final step right here, where I get rid of the protecting group, is also known as a deprotection step. In this case, that deprotection is accomplished by a hydrolysis reaction. One other protection to consider is OH groups. We're going to think about it here as in alcohols, and on the next slide in carboxylic acids. And alcohols are protected by turning them into silyl ethers. Okay? So we can take an alcohol and protect it with tert-butyl dimethylsilyl chloride, which is a mouthful, so it's typically abbreviated as TBDMS. Okay, TBDMS, tert-butyl dimethylsilyl chloride in this situation. So TBDMS chloride, right? Our alcohol, it's a simple SN2 reaction, which might seem like a problem at first, right? How am I doing an SN2 reaction with something that's tertiary? But you can actually do those when your middle atom here is silicon, not carbon, because the bonds are a little bit longer. So it does allow that reaction to happen. Protect the alcohol by turning it into a tert-butyl dimethylsilyl ether. So now I've taken my alcohol, converted it into an ether, and now I'm safe. This is some more chapter 11 type material. Okay, so don't worry about that. But from this slide, I do want you to know that you protect an alcohol by turning it into a silyl ether using TBDMS, right? Be on the lookout for that abbreviation. Then at the end, right, you can hydrolyze off the TBDMS ether and turn it back into an alcohol. How about protecting an OH group in a carboxylic acid? Yep. So here I've got an alcohol and a carboxylic acid. This is the OH that I want to protect and carry on to the end to convert to a dicarboxylic acid. Yep. I can do that. How do I protect an OH group in a carboxylic acid? Well, I convert it to an ester. Okay. Then I've got something that's less reactive down here, and I can carry my reaction forward, right? After I convert it, then I've only got one OH group here, so only one thing is going to react with thionyl chloride, right? My previous OH, now an ester, is safe. And again, I can hydrolyze it at the end to take it back. The only other thing to keep in mind from 16.10 here, our discussion of these protecting groups, is anytime you're adding a protecting group, it does always add steps to your synthesis, and nothing's perfectly 100%. So anytime you're adding steps to your synthesis, you're also reducing your yield. So you wouldn't ever choose to use these unless they're completely necessary. Chapter continues in 16.11 discussing sulfur as a nucleophile, getting back to some other reactions from the chapter. 1611 talks about the reactions of aldehydes and ketones with thiols. Okay? And we will summarize this chapter, this section anyway, in a couple of words. Aldehydes and ketones react with thiols, okay, which is the SH, to form thioacetals, which is just taking the acetal we've seen before and replacing the oxygen with sulfur. Okay? The mechanism's the exact same. Everything else is the same. The only real use for these things is a process known as desulfurization. Yep. And desulfurization takes a thioacetal here, right? This is the most common use of Raney nickel with hydrogen, and it reduces down to just a methylene carbon here. So the synthetic utility is as an intermediate in converting a carbonyl down to a methylene carbon. And that brings us to 16.12, reaction of aldehydes and ketones with a peroxyacid. Okay. You should recall peroxyacids from last semester. We used them in epoxidation reactions. And now we're dealing with the conjugate base of a peroxyacid, right? So it looks like a carboxylic acid, but it has an extra oxygen. And because it's the conjugate base, we've lost the hydrogen here. Right? Aldehydes and ketones react with the conjugate base of a peroxyacid to either form a carboxylic acid from an aldehyde or an ester from a ketone. Okay? All they're doing is it's inserting an extra oxygen. That's an easy way to remember it, right? Aldehyde inserts an oxygen here, forms a carboxylic acid. Ketone inserts an oxygen here, forms an ester. Okay, so because we're adding oxygen, it's an oxidation reaction. And the most common synthetic tool here in the Baeyer-Villiger oxidation, which this is a named reaction. Okay, remember what we said about named reactions, important to pay attention to. Right, the most common thing you use for the Baeyer-Villiger oxidation is this peroxytrifluoroacetate. That's what this guy's called. So be on the lookout for them. You see peroxytrifluoroacetate here, boom, you know it's a Baeyer-Villiger oxidation. What's that mechanism look like? Okay, first step should look the same. Okay, I've got this nucleophile coming in, attacking my carbonyl carbon. These pi electrons are shifting up. The big difference here is when I bring this lone pair back down to reform the pi bond, then I have what's known as a migratory group, right? Which kind of is like a methyl shift that we saw with carbocations, right? If I could form a more stable carbocation by a methyl shift. This group, instead of just, acting as a leaving group, shifts over to the oxygen, okay? Because this is an unstable intermediate. We can get more stable products over here by making that happen. And these migration tendencies dictate where the oxygen ends up being bonded to, which is important if your ketone wasn't symmetrical to start with, right? Over here, for example, cyclohexylmethylketone, right? Not symmetrical. So do I put the oxygen in this bond or in this bond? Right? Two possible products. And it turns out that the one on the right is our product here, because as you can see, right, a secondary alkyl group moves easier than does a primary alkyl group, right? This is a primary alkyl group. This is a secondary alkyl group, okay? So it can move faster. How is that group determined, right? Just one carbon primary alkyl group over here, looking at this carbon bonded to two others, right? That's a secondary alkyl group. That can move easier than this one can, so that's why this gets the oxygen. If we had a tertiary group or a hydrogen in there, those would be even better. They would get the oxygen. Okay, so Baeyer-Villiger oxidation. Definitely be familiar with that from chapter 16. Another important named reaction, the Wittig reaction. Wittig reaction, right, takes a ketone or an aldehyde with this guy, which is known as a phosphonium Ylide, and it forms an alkene. Okay, so an aldehyde or a ketone reacting with a phosphonium Ylide to form an alkene. And effectively, all this is doing is interchanging the double bond from the carbonyl, right, that group, and the double bonded group from over here. Okay, we're switching them, switching the yellow and the purple over here. And it's driven by stability of these phosphorus-oxygen double bonds. How is this thing formed is the first question. Phosphonium Ylide. Okay, mechanism is down here. It's just a simple SN2 reaction, right, between triphenylphosphine and an alkyl halide with however many carbons you're trying to get. Then you need a strong base here. Okay, so we're using butyl lithium to deprotonate one of these hydrogens. That makes my phosphonium Ylide. You do not need to know the mechanism for forming the phosphonium Ylide. You just need to know how to identify it. And notice up top here, it's shown two different ways. The definition of an Ylide, right, is something with opposite charges. You see here the positive and the negative on adjacent atoms that both have complete octets. So this is the true form of the phosphonium Ylide. You also see it represented this way, which is fine because remember, phosphorus can exceed the octet. It can go hypervalent. Okay. So know what the phosphonium Ylide looks like. Know the mechanism of the Wittig reaction. Okay. It's a concerted reaction. Hopefully you remember that term, everything happening in concert. And it's a 2+2 cycloaddition. Okay, we saw that in like the Deals, all their reaction, a cycloaddition, right? This cyclic intermediate. So what's going on? Right, starts here from my nucleophilic carbon from the Ylide, gets added to my carbonyl carbon, right? And then instead of this pi bond breaking and going up to oxygen, it goes straight over to phosphorus, right? Which is looking like a good electrophile with that positive charge to form my cyclic intermediate here. Okay. Then I do a simple switching to eliminate this triphenylphosphine oxide, that's called, and that forms my alkene. This is a really powerful reaction, right? Gets the name, gets the synthetic utility because it's 100% regioselective. I can selectively form some tricky alkenes this way, which is shown in this slide right here, right? How could I make this kind of alkene, which is a less substituted product? So even if I start, right, with a tertiary bromide or a primary bromide over here, in these reactions, these eliminations, right, it's always showing up as the minor product. So the Wittig reaction is the only way to make this be a major product. It's completely regioselective. It only forms this alkene. Right? It's one of the best ways to make a terminal alkene like this as a major product. The big thing you need to consider when you're designing the reaction, right, choosing your reactants for a Wittig reaction, right, I've got two possibilities because if I'm doing a retrosynthesis, right, I'm just breaking up this bond and one of them's going to the oxygen from the carbonyl, the other's going to the phosphorus from the Ylide. Okay? So which one do I choose? Right? And the rule right here, Ylide should come from the less sterically hindered alkyl halide, right? Another way to put it, right, is your Ylide itself should be less sterically hindered. So here with a hydrogen and an ethyl group, that's preferable to having the two ethyl groups, right? You want the least steric hindrance, aka having the smallest groups being on the Ylide, the carbon that's double bonded to the phosphorus to start. Okay? And that just helps the Ylide be prepared from that SN2 reaction. That was on a couple slides. So two important reactions, right? Summary from this video, know protecting groups, know how to protect the OH in an alcohol, know how to protect the OH in a carboxylic acid, right? Know the function of acetals to protect ketones, know the Baeyer-Villiger oxidation, know the Wittig reaction. Really key ideas from chapter 16.